Hello everyone, we are Team Elysium, and today we are proud to present our project, the Smart Greenhouse IoT Control System for Optimized Agriculture. Our project is designed to showcase how technology can transform from traditional farming practice into a more efficient and sustainable operation. Let's take a look. As global food demand continues to rise and available resources shrink day by day, there's an urgent need for innovative solutions in agriculture. Traditional greenhouse farming often need help with issues like inconsistent environmental control, high resource usage, and labor-intensive practice. While our smart greenhouse project utilizes IoT and AI to create an automated, data-driven system that addresses the challenge. The system aims to support farmers by providing optimal growing conditions, boosting yield, and conserving resources. Our project set out with three main requirements. First is IoT integration, to ensure a continuous, real-time monitoring of environmental factors, an AI-driven automation to implement adaptive algorithms that analyze data and automate adjustment to irrigation, ventilation, and lighting. Last but not least, we care about our user. We develop an intuitive central dashboard that offers seamless data visualization and remote control of greenhouse operation. These requirements were foundational to create a system that not only automates process, but also makes the management of the greenhouse easier and more efficient to user. Our mission statement, to quote, is to enhance greenhouse management through a comprehensive IoT control system that supports higher yield and sustainable practice. The objectives include, first, ensuring efficient and precise control over temperature, humidity, and soil moisture level, to leverage data analytics for both predictive and real-time environmental adjustment, to simplify the user interaction through an intuitive interface that provides clear data visualization and control options. Allow me to introduce our team. First, we have Nguyễn Lê Trường Thi, who is our project manager. Me, Lê Nguyễn Anh Duy, is software engineer of this project. Văn Phương Anh, our data engineer. Nguyễn Anh Duy, our UI UX designer. And last but not least, Phan Công Hưng, our AI specialist.
Okay, now let's move to the next slide. So to ensure our system meets the diverse needs of each user, we develop personas that reflect the goals, challenges, and values of three primary stakeholders. So the first one, as we can see here, is the Elon Musk, the you-know-who, stand for the technology provider. Elon's focus is on innovation, scalability, and environmental impact. For him, Elysium is an opportunity to lead agriculture transformation, integrating AI to reduce resources use. He envisions a future where technology-driven, sustainable farming practices can address food security challenges globally, aligning his vision of high-tech, eco-friendly solution. And the second person is Scott Angel, a greenhouse operator. Scott emphasizes day-to-day efficiency. His priorities include easy system manageability, real-time monitoring, and minimal manual interventions to manage resources like water and energy, which is very essential. Scott needs Elysium to reduce operational costs by automating processes and providing data insights that allow quick adjustment. This efficiency contributes to his goal of sustainable production with minimal environmental impact. And the last one is Thomas Hoof. As a traditional crop farmer, Thomas sees technology as a way to enhance, not to replace, natural growing rhythms. His focus is on producing premium quality crops sustainably, and Elysium's IoT monitoring helps him align with each crop growth needs, while predictive analytics aid in anticipating and minimizing issues related to weather and soil conditions, allowing for a blend of traditional and modern approaches. So together, these personas help us design a system that balances cutting-edge tech, easy-based operations, and a sustainable approach to farming. Okay, so let's move to the next slide is the diagrams. So the first one is ELYS, which is stands for the entity relationship diagrams. To build an efficient and well-integrated greenhouse management system, we developed a series of entity relationship diagrams progressively and tailored to the system architecture. It transitions from a high-level conceptual framework to a detailed and fully implementable database design. This design forms the backbone of our greenhouse monitoring and control system, ensuring efficiency, scalability, and robust functionality. Okay, let's begin with the conceptual design. At this stage, we focus on the foundation structure of the system. The core entities, greenhouse, users, and sensors are identified and their high-level relationships are mapped out. This design highlights the three primary processes. Monitoring is real-time environmental data collection, maintenance, manual or automated system updates, control, adjustments to greenhouse conditions triggered by data or users. And the goal here is to ensure the modularity, scalability. For instance, as we add more greenhouse or sensors, the system should seamlessly adapt. It's also flexibility. Each model operates independently, but integrates smoothly for a cohesive system. Okay, next we move to the logical designs. Here the relationships between entities are expanded, and we define attributes for each table. For example, greenhouse includes attributes like location, size, and crop type. Sensors included type, installation date, and status. Users capture roles, login credentials, and activity logs. At this stage, we focus on core models like monitoring and control, which are tied directly to IoT sensors and actuators. Data normalization is to minimize redundancy while preserving critical relationships. Logical relationships, for example, one greenhouse can have multiple sensors, but each sensor logs data independently. So This logical design ensures that the database structure is not only functional, but also optimized for storage and query efficiency. Okay, finally, we reach the physical design, where the logical structure is translated into a detailed and implementable database scheme. Key features include: the first thing is tables and keys. Primary and foreign keys are defined to enforce robust relationships. For example, sensor ID is a primary key in the IoT sensors table and a foreign key in the sensors data table. Constraints. So these also include the unique constraints to avoid duplicate sensors installations, and check constraints to validate the data entries like temperature ranges. And the final is indexing and partitioning, critical for performance high-value tables such as sensors data, and partitioned by the timestamps or greenhouse IDs, ensuring quick retrieval and scalability. Also, there is some performance is further enhanced with like triggers and procedures for automating alerts and system response. Materialized views, these allow real-time summaries of data without the need for frequent database queries. And we also have the balancing factors across levels. At every stage, we kept our 4 key considerations in mind, that is modularity, scalability, data integrity, and the performance. For modularity, each module, monitoring, maintenance, and control operates independently but integrates seamlessly. For scalability, the design anticipates growth such as additional greenhouses or more sophisticated analytics model. For data integrity, relationships and constraints ensure the consistent and reliable data across the system. And the last one, performance, for optimizations like indexing, triggers, and partitioning to ensure the system remains efficient even under heavy workloads. In conclusion, our ERD evolves from a high-level conceptual framework to a detailed physical design. This progression ensures the system is not only functional and scalable, but also robust and efficient. With this design, we've created a solid foundation for real-time monitoring, predictive analytics, and dynamic control, paving the way for smarter and more sustainable agriculture future. Thank you.
Let's continue with the data flow diagram. The data flow diagram is crucial in visualizing how the data flow through our smart greenhouse system. Illustrate the interaction between components and how the information is processed at each stage. At the context level, the DFD highlights the interaction between the greenhouse and the external entities, such as operators and IoT devices like light sensor or temperature sensor. It shows the main data input and output, providing a macro view of how external systems fit into and receive the data from the greenhouse system. In the second level, which is top level, this diagram breaks down the internal process more specifically, showing how the data is collected from the sensor. It details how this data is transmitted to the central processing unit, where initial analysis and filter occurs. The processed data is then relayed to the control system, which make adjustments such as triggering automation irrigation system, or can be sent to the user dashboard. And the last one is detail level DFD. This level provides a comprehensive look at the system inner working. It shows intricate interaction between different modules, such as how the AI model collects data from the sensor. For example, temperature and humidity data feed into the AI algorithm, which processes this input in real time to decide whether to activate the climate control measure or automatically adjust the greenhouse system if needed. The diagram also illustrates how processed data is forwarded to the dashboard, ensuring user receive up-to-date information and notification. This diagram were instrumental in defining how data would be processed and relayed throughout the system, ensuring optimal real-time response. For instance, understand the path of the data flow help us fine-tune the system for quick response times, critical for maintaining crop health. Additionally, the detail level DFD allows us to verify that each component could communicate effectively with each other, minimizing the risk of data loss and miscommunication. Overall, the DFD were not only essential for the system design, but also serve as a guide for implementation, ensuring that every step in the process will account for and that data integrity and flow will maintain throughout.
We conduct a risk assessment to identify the potential issues and mitigation strategies, and we have defined 3 problems that we have considerable is the sensor failures, mitigate by implementing regular maintenance schedules and having redundant sensors, AI model inaccuracies. We will address this will address by continual training of AI model with updated data. Also, the data security concern we will manage with encryption protocols such as SSL, TLS for data transmission, and AES for data storage. So by anticipating these risks, we ensure that our system would remain robust and reliable under various conditions. I'm Phương Anh. I will talk about the major specific technology. The first one is IoT sensors. Our smart greenhouse system relies heavily on IoT sensor, and we use many technologies to build the greenhouse system. Especially the first one is central unit Raspberry Pi is the core processor of our system. The temperature and humidity sensors H8030, these sensors are very critical for maintaining optimal air conditions. The next one is light sensors PH17500 monitor light intensity to ensure plants receive the appropriate amount of light. Soil moisture sensor V1.2 track the moisture level of soil to determine when irrigation is necessary. CO2 sensor MHZ19B monitor the carbon dioxide level to optimize the photosynthesis and plant productivity. All the sensor is transmitted to the central unit via secure Wi-Fi and Bluetooth connections. The next one is our automated irrigation system. This will help us to adjust the water usage by the AI algorithm will process the data from the soil moisture sensors, temperature, humidity, and weather forecasts to control the water distributions. This system contains of the electric submersible water pump, ensure even and efficient water distribution across the greenhouse. The next one is the US solid brass electric solenoid valve, control water flow to specific zone, enabling precise irrigation management. And the solar panel will provide renewable energy to power the irrigation system. And by optimizing the water usage, this system supports sustainable practice and maximizes the resource efficiency without compromising crop health. The next one is our AI algorithms. AI is at the heart of our ultimate system. We use several frameworks and techniques to develop machine learning models that predict the adjust conditions. And we utilize popular frameworks such as TensorFlow, PyTorch, and Keras to build and train our model. Python and or were essential for data analysis, while JavaScript help with integrating AI function into the user interface. We also use the platform like Apache Hadoop and Apache Spark to process the large sets of historical sensor data for model training. And the AI model we use here is the decision tree and regression that can enable the system to predict the optimal conditions and trigger the adjustment to the HVAC system and irrigations. So the model will allow for the ultimate decision making, minimize the need of manual interventions, and ensuring the greenhouse operates efficiently and adaptively. The next one is data analytics and management platform. So the data analytics and management platform centralize the real-time data on climate, soil, and crop conditions. So this approach will enable the comprehensive view of all data stream for immediate actions. So we use MariaDB for structured data management and AWS for scalable cloud storage. Also, we have RS485 protocol that will ensure robust and long-distance communications between the various system components. Also, the SBI protocol used for high-speed, efficient data, high-accuracy transfer between sensors and the central unit. This protocol ensures seamless communication, allowing the system to process data and respond in real time to changing the environmental conditions.
And the final one is our climate control system, which is integrated with a user-friendly dashboard and an AI-powered website that supports real-time operations. About dashboard features, offer real-time visuals of current environmental conditions, user controls for manual adjustments, and automated notification for immediate response needs. AI-powered support. The website includes an AI-based chatbot that assists users in troubleshooting and provides guidance for optimizing the system performance. The interface was designed with ease of use in mind, allowing operators to quickly make changes, monitor greenhouse conditions, and receive updates that facilitate proactive management. Now we will move to the website. Come to our website. Our system includes a dynamic and user-focused website designed to introduce our project and its cutting-edge capabilities to prospective users and collaborators. The website consists of 6 key pages: Home, Jobs, Apply, About Us, Technologies, and Support. This is our homepage, which is an engaging overview of our mission and project goals, welcoming visitors to explore more. And we also provide our service packages for anyone who wants to use our greenhouse services, which are basic and pro. Next one is our jobs page, which is a dedicated page listing available positions with detailed descriptions for those interested in joining our team. To apply to our company, the Apply page is a user-friendly application form for prospective collaborators and team members to express their interests easily. Here is About Us page, which shows insights into our team and visions and the impact we aim to create through innovative greenhouse management solutions. And the next page is our technologies page, which is a showcase of the IoT and AI-driven system powering our advanced greenhouse operations with in-depth resources on their application and benefits. This is our smart dashboard. And last but not least, this is the support page, which is a specialized tab featuring ELYS AI, our customized AI assistant powered by GPT 3.5, designed to support greenhouse operations. ELYS AI assists users with real-time guidance, troubleshooting, and in-depth answers tailored to the specific needs of our greenhouse management. And here's the demo. ELYS AI can easily answer my question. Our website is developed using HTML, CSS, and JavaScript with animations and dynamic elements for an engaging user experience. This AI chatbot offers seamless integration, providing real-time support and personalized assistance to users. This chatbot enhances the overall user experience by answering questions, guiding users through resources, and supporting system operations. By combining intuitive design, robust technology, and tailored AI support, our website serves as an essential platform for communication, engagement, and operational excellence. The next one is our login page. And here is our login page, which is designed to ensure secure and seamless access for all users to our dashboard. The key feature is account authentication, which ensures that only registered and authenticated accounts can access the system, protecting sensitive data and functionalities. If you enter the wrong email password, you cannot sign in. Only authenticated credentials can log in. Now I will use my account for demo. And here's the remember me tick box. If you tick it, it will store the local credentials on your computer, and the next time when you open that, you don't need to enter your account again. And here, now we can log into our dashboard. The dashboard is the centerpiece of our system, offering users a comprehensive interface to monitor and manage their greenhouse environment. Built with cutting-edge technologies like React, Tailwind CSS, and Vite.js, it ensures a seamless, responsive, and efficient user experience. Here are the key features. In the main tab, which is the dashboard, there will be real-time data visualizations, our charts, system performance, the weather charts, CPU and memory usage over time, network status, last maintenance record, and here's the control panel. The user can manually adjust critical settings like temperature, humidity, light intensity, CO2 levels, fan speed, and can do some quick actions like ventilate, water plants, or turn on and turn off lights. And you can also set up lighting schedule for day and night if you want. And a real-time statistic chart for continuously checking the data of the greenhouse. And the next tab is our alerts tab. We will show the alerts from the system components. And there will be recommended action. You can take action or just acknowledge and perform further action later. And here's the maintainer record page. We will show the records of maintaining our system. And you can also search for the records you want. And you can also follow the performance report. It will be shown based on the average statistic of each month. And here's the tables. You can generate PDF or print reports. And the last one is the settings. There will be basic settings. You can change the theme light and dark, the temperature unit, and also the account settings. Then you can change your password. And then you can reload the page here. Your photo has been changed. And you can also toggle the theme using the button in the dashboard page. As I click the remember me, so now my email and password will be stored, and I do not need to enter everything again. And I'll just log in and use password.
To test and develop our system effectively, we create a comprehensive set of dummy data stimulate real-world greenhouse conditions using tools like Mockaroo for data generations, MariaDB, and MySQL Workbench for database design and management. This we use for validating system performance testing SQL queries. The dummy data includes simulate sensor readings such as temperature, humidity, and light intensity spanning various time periods to replicate real-world scenarios. We use PHP admin, MyAdmin for database interactions and Mockaroo advanced features to create meaningful relationships between tables. We ensure a robust data set. It will allow us to troubleshoot and refine the potential issue in the system before deployment. We also can test and confirm that our AI model could make accurate predictions based on the realistic data inputs. Also, we can enhance system capabilities. So this tool and technology work together to provide a solid foundation for rigorous testing and system optimizations. And next one, I will talk about our use cases. Key use cases include real-time monitoring and reporting. We develop the optimized SQL queries for this purpose. For example, we have queries that can display the top 10 largest greenhouse, so recent alert for the active technologies, identify the greenhouse using specific technology provider. Also, we can see the actuators that link to the control system, summary of the environmental condition in the greenhouse user access with mobile applications. Also, that the greenhouse managed by specific user maintenance records active sensors. This will ensure the structural support efficient and scalable data retrieval. The SQL queries were designed for both speed and accuracy. Next is to enhance our project process. We use various collaboration tools to maintain project efficiency. First one is Confluent. Second one is Jira. Third one and fourth one is Bitbucket and GitHub for update the code version. And Trello is for tracking our team productivity. We want to develop our ongoing skill for our project, so we go to LinkedIn Learning. And Microsoft Teams is our communication channel. The Jira timeline lighten key milestone, task assignment, and process tracking. This tool helps us to visualize the project phase and ensure timely completions. We have 5 sprints, and now we are in sprint 2. Additionally, our team help monitor on Trello, provide transparency, helping us to quickly identify and resolve the potential roadblocks, help to improve our team productivity. This proactive approach allows us to keep the project moving forward smoothly and maintain high productivity.
The expected outcome include a 30% reduction in manual intervention, a 15% increase in crop yield, and a 20% reduction in resource usage, contributing to cost saving and sustainability. We have also learned valuable lessons, such as the importance of team collaboration and maintaining a clear communication. Technically, it's between balancing data normalization and denormalization are key to optimize our performance. Finally, we apply ethical consideration to ensure data security and user training. In conclusion, our Smart Greenhouse Art project utilizes IoT and AI to revolutionize greenhouse farming. Moving forward, we aim to expand this technology to support a broader range of crop and environmental settings, further contributing to the global push for sustainable agriculture. This is our contact info for if any of you want to find more about us. Thank you for your attention and your listening. That's all.